Communication, triplet from the Jamia Millia Islamia, New Delhi. Dr. Nizam is working as Associate Professor in the Department of Electronics and Communication Engineering at Jamia Millia Islamia from March 2017. He is also Deputy Nodal Officer, National Academic Depository Cell at JMI. Earlier, he has worked in Baba Ghulam Shah University, a state university in Jammu Kashmir, and Mebat Engineering College under the Haryana Waqf Board, and Galgotia Engineering College and Al Falah University before joining the Jamia Millia Islamia. Dr. Nizamuddin sir got several Best Paper Awards in the reputed international journals and conferences, and he has published a patent also. His work has been published in more than 70 reputed journals and conferences. He has also worked as a training and placement officer at Mebat Engineering College from 2012 to 2016. His field of research include VLSI devices and nanoelectronics, circuits, and the embedded system. Without further ado, I request to Dr. Nizamuddin sir to take over this session on the topic of CNTFET, devices of future nanoelectronics. Sir, please.
With the permission of chair, I would like to share my presentation, please. First of all, I would like to thank the organizers and the administrative members of SRM Institute, who has given me an opportunity to explore the work which I have done and to tell the energetic researchers who are working in this field. So my thanks goes to Dr. Sanjay, who is the registrar of SRM Institute, and the Dean Devendra Kumar Sharma ji, and Professor Pankaj Singh, who is the head of department, and one of the important person, Mr. Arun, who was in contact with me for last 1 week and has given me an excellent response. And finally, I would like to thank my friend, Dr. Prashant Mani, who is basically inspiration for me to be the part of this FDP. Apart from it, we should also thank AICTE, who has given a lot of fund for organizing ATAL FDPs, which are very important for our faculty members and researchers, especially in this pandemic situation. So the topic of my FDP would be CNTFET, which is basically a device which I would like to explore in detail, a device of future nanoelectronics. Basically, in this talk, I'm going to discuss about electronics device objectives. What should be the objective of an engineer while we are going to design something new? We know well that there are two important aspects of an engineer. If you are going to design something new, or if you are going to add something in the existing system, only these two are the job of an engineer. Rest of the things, just to repair the things, are not the part of engineering, or to compare the thing with a little bit modification, maybe the initial stage of engineering. So we must keep the electronics device design objectives in mind while we are going to design something new. As I have mentioned that the talk of my talk would be on CNTFET, which is a modern device. So what's the need for having these devices or the other devices which are very important part of the future nanoelectronic circuits? So the reason behind is it setback of MOSFET. Then I would like to explore the carbon nanotube, which is the basic element or the material of CNTFET, its properties and its major application in terms of CNTFET. Later on, I have published few papers which are based on CNTFET. I would like to explore them, and one of the paper is based on OTA. And how to compare one work with the another one which can also be published in the same family members. Like we have, I have published one paper on OTA. It has been compared later on with another modified version of OTA, which is Cascode OTA. So after comparison of these two, it will be very easy for young engineers who are here how to compare the things and to publish in the reputed SCI journals. That's why I'm taking the comparative analysis of both OTA as well as Cascode OTA. And finally, there would be the conclusion. From this tabular description, I would like to tell you that the device, is my cursor visible to all of you? Please let me know. The movement of my cursor is visible or not? Any one of you, please? Hello?
No, sir.
No.
No, sir. No, sir.
Is it visible now?
Yeah, right now.
Okay.
Yeah. Right now.
Yes.
It is.
Okay. Right. So I will not keep it in full screen. Now we will start from CNTFET. Okay. Apart from this CNTFET, there is one more step which is CNT. You know well, CNT is a material. Okay, like silicon is a material. How to get electronic grade silicon is the first step in electronics engineering. And finally, from this silicon or electronic grade silicon, we design devices. So similarly, from CNT, we are going to design a device which is called CNTFET. Okay. Or from this device, this is a device level, okay, analysis. And then from this device, we will design circuits. So circuits which have been designed using this CNTFET are CNTFET based OTA and CNTFET based Cascode OTA, which we will discuss later on. And finally, using these Cascode OTAs or simple OTAs which are based on CNTFET, we will implement in electronic circuits. And the circuits are filters. So our discussion would be from device to circuit level only. A little bit discussion will also be from material, which in terms of CNTFET. Okay, so we are covering three aspects: device, circuit, and before it, material. And you know well, there are level of abstraction in VLSI design. First we see the material, then device, then circuit, and then system in terms of its implementation. So we are not going to discuss anything about system level. As I have told you, these are the key design objectives which we must keep in mind while we are going to design something new. Whatever we have designed, it must be compact, compatible, consume less space or minimum, or the density should be as high as possible. Another important aspect in latest technology is power consumption. We prefer large battery life and less thermal issues. If suppose we have reduced a power level up to maximum of the possible design values, but if it is not fulfilling our requirement, or if it is having thermal issues, it's not preferable. We know well, if there are people from VLSI background, at present the research level is reduced to threshold region. Or what we are designing electronics devices in sub-threshold conduction region only. The device is not turned on. We are not turning device on above threshold voltage, and the purpose is solved. The zero value is considered to be low, and the voltage which is very close to threshold voltage is considered high. So if such a small voltage is being considered for switching on or off our transistor, which ultimately fulfills our digital electronic circuitry performance, so we can understand that the importance of this power consumption level. Apart from this power consumption, speed is also an important factor in today's electronic gadgets. So of course we will prefer less delay. The delay should be as low as possible, and correspondingly the fast response is desirable. Apart from it, functionality, more throughput, more functions should be possible using the proposed circuitry. Of course, finally, we must keep the things which we are going to design. We must keep in mind that it should be readily available to the people who are underprivileged conditions. That is also important factor. Of course, we know well that there was a revolution in the electronic industry while we were able to develop microcontrollers. And after the invention of microcontrollers, there was a huge cost reduction in the electronics industry. So similarly, that was an achievement. So while we are going to design something, it must be cost effective. And of course, noise margin is, gain margin is also important factor, but I have mentioned especially the noise margin, because the noise margin is very important. In most of the cases, we are designing electronic circuitry based on digital techniques, but our environment or our world is, or we people are feeling analog signaling. So how to interpret with this analog signaling, or how to interfere, how to basically use our proposed models, proposed system in the analog world, because the world is analog. So we have to design a system or a circuit or whatever we are going to propose in terms of electronic gadgets. It must have large noise margin. And finally, reliability is very important apart from long lasting. Aging factor, you know well, aging factor is very important. If our device will last long, it will be effective. Okay, and the people will prefer it. So these are the few design objectives which we must keep in mind while we are going to design our electronics circuits. Now,
what is the this variation?
Hello.
In reliability section, you mentioned pressure variation.
Reliability, actually what happens, if suppose we are going to design something new, it must be optimum so that the external effect like the temperature and pressure variations while we are fabricating an IC, okay, so external environment should not affect the devices, or while we are using our electronic gadgets. For example, there are two things. While we use two type of electronic gadgets, one for domestic applications and another for military applications. So the range of temperature variation for the devices which have been fabricated for military application is different one as compared to the domestic one. So whatever range we have considered, it must be optimum. It must lost
So my doubt is whether you this pressure term is the process variation, or is it pressure only you want to say?
Yeah. No, process variation will also be a part of it. Process variation will be the part while we are manufacturing it. In this term, we are basically these electronic design objective in terms of reliabilities once the product is in the market.
Okay. Okay, but when it is in application, okay.
Yes. Okay. Now the real thing starts from here. There are two things. First is dream and its realization. We know well these are the two reputed people of the world in our field. Richard Feynman's dream is being realized at present, and we are seeing, okay, it is very much known to all of us. What was its dream? He has dreamed that why not the entire Encyclopedia Britannica should be on a head of a tip. So today it is very much possible we can have n number of libraries in a flash on a simple pen drive. And also the Goldsmiths, who has predicted two laws. First law states that which is based on memory, and another one and apart from microprocessor. What it states, the number of transistors on ICs doubles every 18 months for memory and 24 months for microprocessor, which is very much possible at present. And The second one is the average cost of fabrication laboratories for manufacturing ICs increases by a factor of 2 every 3 years. So these are the two important laws which has been basically proposed by Gordon Moore's. We can see here the important point which I want to explore from these two things is bulk technology. Using bulk technology, these two predictions are not possible in future. So to keep the Gordon Moore's law alive, we have to look after the alternates of bulk technology. If we will not see the alternates of bulk technology, we are not going to meet Gordon Moore's law in near future. So that was the ultimate intention, and this is becoming very much possible if we are replacing the current bulk technology or CMOS, silicon-based CMOS technology by alternate technologies. Initially, this is the beginning of realization of Gordon Moore's and Feynman's dream. And it was started with silicon-based technology or the conventional technology. We know well that the conventional technology, which is very mature technology and is still in most of the electronic gadget, it won't be wrong to say that in 98% of the electronic gadgets are based on this bulk technology at present. Although we are having other technology-based devices, which I will explore later on, this is the mature technology. The most important feature or the aspect of this bulk technology, or we can say that CMOS technology in other terms. This CMOS technology or bulk technology is being used in today's time also due to its maturity. And the most important factor of its maturity is nothing but silicon. We know well, silicon is being used in most of the electronic gadgets, or most of the devices are manufactured based on silicon. We know there are general questions. Most of the people are teacher here. We generally ask with the student what's the reason for using silicon as in most of the cases. So it is a general answer of the student at it is readily available. It is cheap. But for researchers, for the people who are reputed people who are in this discussion with me, the most important reason behind the silicon's utilization in most of the electronic gadget is maximum publications. Silicon is the only semiconducting material which is having maximum research publications as compared to other semiconducting materials. What does it mean? Maximum publication means we know each and every aspect of silicon. We can use it without any hesitation. If everything is known about a particular material or a particular thing, so we can easily adjust it in our design. Other semiconducting materials are having limited number of research papers. So this is the most important and the important reason that silicon is still the dominating material in electronics device fabrications. Apart from it, it is having low cost. As we will see later on, in latest technologies, the most important thing is fabrication cost. If we are going to replace our existing technology, so not only the material, not only the device, but the fabrication techniques should be innovative. And the laboratories setup should also be modified or the advanced one. Only then we can compete with the existing technology. So to bring the latest technology to be a big competitor of the bulk technology, we need a large amount of money. So that's one of the reasons that it is due to the low cost of bulk technology, it is still alive. And of course, thermally efficient. This is another important factor because thermal efficiency is very important, and especially in case of military applications. But we cannot survive with the bulk technology in near future. And the most important region is short channel effects. Well, we are going to reduce the size, okay, channel size, okay, while we are going to reduce this channel length, so of course the short channel effects will occur. And these short channel effects are having very adverse effect on the performance of bulk technology. So of course we need to have a bulk alternate of these technologies. Apart from is reliability issues, leakage, and high power dissipation. High power dissipation means a power dissipation which is very high in comparison to the power dissipation if we use the latest technologies. So keeping in mind all these factors, we need alternates. And it is observed that at nano scale, we are not going to fulfill our requirement if we will use this CMOS. So it is basically a shrinking ship. Now, why do we need advanced technology based devices? A little bit discussion has been completed. Now the question is, what are new devices? What are the promising devices which could be the alternate of CMOS? So I have mentioned the most prominent devices, and due to the scarcity of time, I cannot explain all the devices in detail, but some other time, if I have time and if you are interested, we can have a good discussion on all these devices later on. My main focus would be on CNTFET only. Briefly, I would like to explain all the remaining devices so that the researchers who are interested to work in this field may think about them as well. This is the alternate of CNTFET, which is called graphene nano-ribbon field effect transistor. And this is a diagram. In this GNR-FET, what we are going to do, actually we are using a single atomic layer of graphene. This is graphene sheet, which is basically spread or which replace the silicon channel by graphene nanoribbon. And this graphene nanoribbon sheet is deposited beneath gate structure, and it will form the channel, or the current will flow through this GNR-FET. So this is the source and drain, and between these two, this is GNR channel, graphene nanoribbon channel. And rest of the things are very much close to CMOS. Later on, I would like to tell you what are the prerequisites if we want to have alternate of CMOS. So one of the important factor for replacing CMOS technologies is structure. Whatever device we are going to propose, it should be, or it should resemble the structure of CMOS. Only then we can use the existing infrastructure or the existing fabrication techniques for the latest technology also. And another one is, which is also the family member of GNR-FET, is GFT. Here we are using simply graphene field effect transistor. Okay, this is very much similar to this structure. Okay, and another one is SET, single electron transistor, which will revolutionize the world. It is in fancy state at present, but still the people are working on single electron transistor. The working principle of this single electron transistor is based on Coulomb blockade. Another important device is which we are going to basically explore for electronic applications is MTJ, magnetic tunnel junction. This is another important element, but it has some shortcomings, and you can see in detail the shortcomings of this device, but still we can club it with our CMOS technology. Along with CMOS technology, we can have magnetic tunnel junction based nanoelectronic circuits. And the last but one is tunnel FAT, which works on the tunneling effect. And finally, the FinFET. This is the diagram of FinFET. In this FinFET, you can see that the channel controllability of the channel is much better. If the controllability of the channel is better, we can control the flow of charge carriers in a better way. So this is the drawback of this FinFET is geometry. It is more complex as compared to CMOS. So this was all about the latest devices, which are basically the focus of current research for the people who want to work in the field of nanoelectronic circuits especially. As I have told you, we have also discussed about electronic design objectives. So keeping in mind electronic design objective, there are a few more modifications or the requirement of devices which are based on nano. Okay, so these are the prerequisite of nano devices while we are going to design them. Most of the things which have been already discussed: scalability, performance, energy efficient, on-off ratio for memory devices especially, gain for logic devices, operational reliability, and final two I have to discuss now. As I have told you in the previous slide, if you are going to present latest technology based devices, or if you want to replace the existing CMOS device with the latest one, or for example CNTFET, so it is preferable in the initial stage of research that infrastructure which is being used by CMOS should also be used by the replaced material or replaced device. In this case, if we are replacing this CMOS by CNTFET, so we should be in the position that the infrastructure which is being used by CMOS should also be used by CNTFET. And similarly, at architectural level also. These are the few challenges which we are facing at present. New techniques are required to predict, optimize, and design. Of course, challenges are opportunities for engineers and designers or professors or researchers. So these are the hot areas. Apart from it, the second line is very important for the people who want to work in the field of biomedical electronics devices. In case of biomedical electronic, there are three important things which must keep in mind. Amplitude will be small, or the signal will be small signal analysis. Apart from it, there are two important things: voltage and frequency. We have to work at low frequency, low voltage, or negligible power dissipation. If we want to use our latest technology based devices for designing biomedical electronic circuits, so we have to keep these 3 points in mind. It must have low amplitude or the small signal analysis, low voltage, and low frequencies. But all these are becoming a big challenge if we are using CMOS technology for biomedical applications, apart from reliability. Because we cannot rely on latest technologies unless and until it is the design or the simulated circuit is also compatible or is having all the design parameters in comparison to the fabricated one. And apart from it, another important aspect due to quantum mechanical effects occurs. Just ballistic transport we will see in CNTFET, tunnel effect in TFET, and quantum interference are predominating factors while we are going to design nanoelectronic circuits. Keeping in mind all these things and trying to replace CMOS, these are the promising things. And there are two different things, as I have already told you. We will discuss these two things in details. The first thing is material and another one is device. If the material is new, of course we may have new device. So carbon nanotube will be used as a material in carbon nanotube filter effect transistor, which is nothing but a device. So in this case, we are going to replace silicon as a material and CMOS as a device. Both the things have been replaced using promising new material and new device. Now let's start discussion on CNTFET carbon nanotube and then CNTFET. This is all about carbon nanotube. Carbon nanotube basically are allotrope of carbon with a cylindrical structure. You see here, these are the two different types of carbon nanotube. This is called single wall carbon nanotube, and this one is multi-wall carbon nanotube, one inside another. This is a carbon nanotube and red one inside it, green, and like this, so on. So you see here what we are having one carbon nanotube inside another. So this is called multi-wall carbon nanotube, and this is single wall carbon nanotube. So these are the two types of carbon nanotubes. And how to get a single wall carbon nanotube is explored here. This is a single graphene sheet or single atomic graphene sheet. Okay. So from this single atomic graphene sheet, we can have three different types of carbon nanotubes. We can roll this single atomic graphene sheet. For example, let us take a case. Let us suppose this is a single atomic graphene sheet. We can roll this sheet at three different angles. We can roll like this. We can also roll like this. And we can also roll like this. Okay. So what does it mean? Keeping in mind the various design aspects, this graphene sheet is being rolled at three different angles. And we are considering these things in detail here. If the indices are of same mm at an angle of 30 degree, if this sheet is rolled at an angle of 30 degree, keeping the indices same, such type of tube is called armchair. If we are rolling at two different indices, this is an index M, another one is N. Okay, so this type of carbon nanotube is called chiral type, and the angle vary from 0 to 30 degree. And another one is if one of the indices is 0 and another one is having finite value, that is called zigzag. Okay, and at an angle of 0 degree. So these are the three different type of carbon nanotube which are obtained by rolling this graphene sheet at three different angles. And thus we can control its chirality. We'll discuss it later on. So now the beauty of this single atomic sheet is, or the graphene sheet is, if we roll it at three different angles, properties are different. And the reason behind different properties is, if we will roll up sheet at three different angles, so band gap, energy band gap will be different. Why the energy band gap will be different? because the energy band gap will be different due to the variation in DOS. Density of a state will be different. Of course, if the EG is different, the property is different. So this is all about how to roll the carbon nanotube and how to obtain single wall carbon nanotube. So we may have 3 different type of single wall carbon nanotubes. Basically, it was discovered by Ijima in 1991. I have told you it may be single wall or multi-wall, but we prefer single wall carbon nanotube. I will discuss later on. Single wall carbon nanotube can be visualized as a sheet of graphite of around 1 atomic thickness. We have discussed now, which is rolled and joined together to form a cylindrical structure. And wrapping of graphite sheet can be represented by pair of indices Nm. And we have discussed it Nm. It could be of different value and Nm in case of chiral type, and it could be N and 0. It will form zigzag. And these two values, if these two values are same, it would be of armchair at a particular angle, chiral angle. Okay, 30 degree here, and this angle is from 0 to 30 degree, and this is 0 degree for this case. So we are having 3 different type of carbon nanotubes. And what is the benefit of having 3 different type of carbon nanotube? I will tell you in the coming slides. So this is all about carbon nanotube. And now let's see the important application of this carbon nanotube. And the most important application, which is the basis for today's talk, is CNTFET. Apart from it, let us see the exceptional properties of carbon nanotube. Metallic or semiconducting, which is the point of discussion, the most important point. I would like a little bit of attention. We know well, at present, we are using 2 things: device of semiconducting material and interconnection of different material. Device of different material and interconnects of different material. If it is possible that both the things are same, so symmetry will be achieved, and it will be very cost effective if we are using same material for both the things, for devices as well as interconnects. And this is the beauty of carbon nanotube. We will use one type of carbon nanotube for interconnects and another type of carbon nanotube for wiring or for devices. Why is it so? Because the property is changing based on chirality, and this is having a different property and this is having different property. So 2 different type of single wall carbon nanotubes can be used for different applications. One for metallic applications, interconnections, another for manufacturing of devices. So this is the biggest benefit of carbon nanotube. As I mentioned in the next point, we will use the semiconducting carbon nanotube for devices, for example armchair, and we will use interconnects using metallic CNTs. Not only these 2 features, another important feature is CNT has about 4 times higher mobility than silicon, which is another important feature. If the mobility is high, of course our speed would be higher. And we need the devices which are having high speed, which are faster. I have told you in my first slides while I was discussing about electronic design objectives, speed is one of the important factor. Another important game of this CNT is diameter, which ultimately controls width. Is control by chirality, which we have discussed later on in the previous one. Apart from it, thermal conductivity is higher than pure diamond. We know well the beauty of diamond, but the conductivity, thermal conductivity of CNTFET is higher than diamond, which is another important thing. Not only this, excellent field emission. Those people who want to work in the field of field emission display, I will advise them to use CNTs, not CNTFET, CNTs in designing FET panels. You can use, this is excellent emitter. Okay, you can use it for only 1 to 3 volt. Okay, as compared molybdenum we are basically using at present. But if we will use CNTs as a field emitter, the performance would be excellent. And Sony has already used CNT based TV, and in the proposed TV, Sony company has presented CNT as field emission. Okay, another important factor which basically correlate with the first point is current carrying capacity. The current carrying capability of CNT is much better as compared to copper, which we generally prefer for interconnection. So all the merits which are required for designing electronic circuitry, I'm using the word circuitry, not device only, is CNTFET. Using the same CNTFET, by rolling at a particular angle, we can have the behavior of metallic nature, and using it for our devices, we can have semiconducting nature. And these two features of CNT basically will replace all the existing CMOS technology. But of course, there are always cons, pros and cons. Okay, work all together. So of course, there are some limitations. And the most important thing is its growth. Single wall CNT with the growth is complex. I'll tell you in the coming slide what's the need for single wall CNTs in designing CNTFETs. And another important point is CNT chirality control, thus diameter control. We know well, as I have told you here as well, you see here, the chirality basically control diameter and which ultimately control width. I will prove it with the formulas later on. So the chirality control is becoming a tough job. In simulation, it is not a tough job. But while we are going to fabricate the simulated model, it's becoming a tough job. Another important issue from a health point of view is CNTs are basically unexposed matter. We do not know its side effect from health point of view. So it may affect our lungs while during the production or during fabrication process. It may affect, although we have all the covering and there are protocols, but still it is a new material, so we cannot ignore its health hazardous effects. And of course, the last point, which is basically in all the cases of, especially in electronics industries, production cost. So
excuse me, sir.
Yes.
Sir, can you do a presentation full screen, because otherwise it is not visible, the text.
Text is not visible. How is it possible?
Yeah, you have to do F5 or some full screen.
Okay. Is it full screen now? Is it visible now?
So this is a larger font, but the previous slide things are written in small font. So.
Okay. Thank you for cooperation. Very nice. Now you see carbon nanotube versus other materials. You see here, the first point is size. We can control its diameter. But I think now you will not feel the movement of my cursor. That is a problem in my system. I didn't care because I'm taking a class after a long time. That's why I didn't care it. अब मेरा cursor का movement feel हो रहा है? Are you feeling the movement of my cursor? No. That is the problem.
No, sir.
भाई तभी तो यार मजा नहीं आएगा ना फिर पढ़ाने में, है ना? Discussion will not be up to mark. Up, I think now you are feeling. Now the font will be bigger. Hopefully, I'm sure. Okay, please cooperate with the font side. So this slide is basically telling you the merits of carbon nanotube. Strength you can see 45 billion Pascal. If you will compare it with the steel alloy, which is having 2 billion Pascal. So this 45 is very high. So we can use for the materials for manufacturing the mechanical devices, mechanical equipment also. Elasticity band without damage. It will not fracture. And the most important thing from our people point of views, its current carrying capacity, which I have told you earlier, is 10⁹ ampere per centimeter square. और copper की कितनी है? 6. So this is another important parameter. Thermal conductivity is higher than diamond, and of course cost will be initially the high. ये मुझे full screen से बताना पड़ेगा आपको. This is the last slide, which will going to explain about the carbon nanotubes. Okay. From next onward, we will discuss about CNTFET only. You see here the first important application which has been discussed in detail. I'm just skipping it. Nanoelectronics devices, and the most important example of nanoelectronics devices is CNTFET. Point number 2, field emission display. As I have told you, this is also the important field of research for electronics engineers who want to work in field emission field. More concentrated electric field is produced at very, very low voltage. Another important example I have told you, SET, single electron transistor, which will decide the future of nanoelectronic circuits. Okay, what happens based on the controllable transfer of single electron between small conducting islands? We have never seen the electrons. I have felt the effect of electron in my nano center at JMI. Jamia is having nano center, nanotechnology and nanoscience center, where we are having AFM and SM. So you can see the effect or the realization of current, but we have never seen. So this is one of the important field of research for electronics engineers. Again, single electron transistor based nanoelectronic circuit design, where a single electrons will be deciding factor for bit 1 and 0, which is beyond imagination, but it is very much possible in near future. Apart from it, wires and conducting composites. We are talking about polymer electronics. It will play a vital role in polymer electronics, wires and conducting composites. Okay, and another important application of carbon nanotube is MEMS. We know MEMS. MEMS is very important part. If we basically talk about interdisciplinary research in mechanical engineering and electronics engineering, so MEMS plays a vital role. You see the airbags in cars. What happens? It opens the complete basically game is behind MEMS. MEMS play a vital role in airbags. Similarly, if we are further reducing the size and further we are replacing the existing electronic circuitry in case of MEMS, the further miniaturized field is NEMS, nano electromechanical systems, where we use CNTFET. Again, we can have batteries. Space elevator is another important field, because there are two things which are very important. I skip this point, so I would like to tell you the 7th point is very important. Space elevator. There is a phrase that if there could be a ladder from Earth to Moon, that is possible using carbon nanotube. From this phrase, we can understand the importance of carbon nanotube. If there could be a ladder from Earth to Moon, that is possible using carbon nanotube. What's the reason behind it? It is having excellent aspect ratio. And what is that? Strength to weight ratio is very, very high. Actuators, we can have quantum computing, hydrogen storage, and all these are the things which are very important. And finally, at last, we can see CNT's biomedical applications. What happens? We basically, there are two things, adsorption and absorption. This adsorption feature of carbon nanotube will play a vital role in biomedical electronics. What happens? Basically, we grow the cells on the surface of carbon nanotubes. If we grow the cell on the surface of carbon nanotube, it will react differently. And then we can use in biomedical applications. And the same thing which is skipped in this slide is application in basically sensors. Carbon nanotube is having excellent applications in sensor technology because it plays vital role in reactions with a distinguished chemical or distinguished gas. So this is all about carbon nanotube. I skipped few of the things due to the scarcity of time. Now, the most important application of CNT is carbon nanotube field effect transistor. इसमें तो मुझे fill screen नहीं करनी है because I have to explain the things. Okay. यहाँ से अगर बड़ा हो जाए, हाँ, yes, very good. You see here. Okay, you see. This is your carbon nanotube field effect transistor. थोड़ी देर ऐसे ही देखते हैं, फिर उसके बाद I will tell you one by one. You see the diagram, please, carefully. In this diagram, we are having source side, drain, and the substrate is of silicon. Above it, we are having silicon dioxide. Adjacent diagram is top view, source, drain, and gate. LG is the gate length. There are few other things which I will like to explain you in the coming slide. Let's discuss a little bit if you can easily understand. There is a term pitch, P-I-T-C-H, pitch. Pitch is inter-Cnt spacing. All these are basically specifications which you must keep in mind while, because if these things would be, if you can easily understand all these things, then it will be easy for you to understand the reason for the variation of response. What's the reason behind the variation in gain? Why the gain is higher in case of CNTFET based devices, or what's the reason for bandwidth, output impedance, and power dissipation. That's why we must know all these design specifications. As you all are engineers, you all are professors, and I may be one of the junior most professor among you people. So if there is a mistake, please pardon me. I'm trying my best to tell you whatever is about carbon nanotube field effect transistor. So there are two things from research point of view. The first thing is design parameters, and then using these design parameters, we obtain response. So design parameters we are going to discuss now of this CNTFET. And the most important design parameter is its pitch. You see, pitch is the inter-CNT spacing. Inter-CNT spacing is the pitch. Okay, there are two CNTs. Side view, देखिए please. You see here, there are 1, 2, 3, 4. There are 4 CNTs in the top view. Of course, so it is mentioned that the pitch is the distance from the centers of adjacent carbon nanotube. Okay, so here LG is the gate length, CNTs, and the width is gate width. So this is carbon nanotube. Now let us discuss its significance or its beauty as compared to the bulk CMOS. The first and the foremost benefit or the significance of this carbon nanotube field effect transistor is ballistic transport. Charge carriers moves like bullet. This term has been derived from that thing. Okay, there is a ballistic transport. Yeah, in other words, you can say resistance-free transport. Ideally, it is resistance-free transport of charge carriers, which results in high mobility. And if the high mobility, and we have discussed already that it has large drive current. So of course, if it is having ballistic transport, there would be higher mobility. And another feature which is due to the CNTFET is large drive current capability. So from all this discussion, the point number one reflects that the CNTFET is having 3 to 4 times higher than bulk technology, mobility or the drive current. Okay, we have discussed already. Another important aspect from designing electronic circuitry is transconductance. Its transconductance is very high as compared to CMOS counterparts. We'll see with the proof in the coming slides. Another important feature is similar working to conventional MOSFET. You see the equations, please. You see the equations here. These are the equations, and the first equation is very much similar to the current flow of CMOS. In this case, you can see N is the number of tubes. You see number of tubes 1, 2, 3 here. Okay, we can change this number of tubes. So correspondingly, the current will be changed. GCNT is the transconductance of a particular CNT. First, second, third, fourth, fifth. Okay, if we will change the number of CNTs, of course GCNT will increase, and this is nothing but drain voltage and threshold voltage. Again, GCNT, this is source length and resistivity of source or drain here. Okay, and second equation is very important. W stands for width. This is your width. Okay, and for number of tubes. If we will increase the number of tube, of course, you see here, if the number of tube is increasing, then the width is also increasing. Again, if we are increasing S is pitch. Pitch is inter-CNT spacing. I've told you inter-CNT spacing. What does it mean? The distance between the centers of two adjacent CNTs. You see, this is, let us suppose, first CNT and this is second CNT. So from the centers of these two CNT, we'll measure, that is called pitch. If we will increase, of course, if you see physically, we can judge from this diagram also that if we will increase this space, of course, the width will also increase. Another important factor is D, diameter. If we will increase the diameter, of course, the width will also increase. And we know well, width is very important factor. Okay, now effective width will be and D and proportionality constant. Apart from it, another important equation is EG. As I have told you, this is another important feature of carbon nanotube. You see here, EG is energy band gap. You see, energy band gap is inversely proportional to diameter. Okay, if we will reduce the diameter, of course the EG will increase. Okay, and of course the property will change, and this is basically dependent on, D is dependent on chirality, and chirality we have we have already discussed the effect of chirality. How to chirality is changing, how the angle is changing, how the indices are being changed. So on on indices, the chirality D depends, and on D, EG depends. So the complete game will be changed. If we'll change the diameter. Now, let us see the three design important parameters of carbon nanotube field effect transistor. As I have told you, the first important is pitch, CNT pitch. Okay. Cnt spacing, I have told you earlier, it is being represented here. Another one is width. Another one is number of tubes. And this ultimately depends on CNT. This is all about the synthesis of carbon nanotube. How can we synthesize it? Keeping in mind the constraint of time, I would like to not go in detail because I have to tell you last 30 minutes remaining. Okay, this is the chemical vapor deposition technique. Okay. In this technique, what we are going, we basically sand precursors, carbohydrates, and this is a board, and this is your sample. And this chamber is heated at a degree of 720 degrees. Okay, and when we pass these precursors, the carbon nanotube is deposited here, and the rest of the things are basically goes out using these outlets. Another method here, the carbon nanotube are basically deposited here. Okay. Anode, cathode, we apply a voltage here. Okay, then the CNTs are deposited here, and this is laser ablation method. In this laser ablation method, CNTs are deposited here. So these are basically the synthesis process of carbon nanotubes. Without delay, I would like to go the designing part. Now, till now we have discussed about carbon nanotubes, about various applications of carbon nanotubes, and the most important application of carbon nanotube in terms of CNT-FET. We have discussed about CNT-FETs, its design parameters, its equations, its features, its merits, and apart from it, the most important, its compatibility with CMOS technology. Now, how to use this CNT-FET in designing electronic circuitry? We will discuss now. Please wait for a while. As mentioned here, still application of carbon nanotube is not explored in analog domain. There is a large scope of designing CNT-FET based analog circuitry, and I have told you for the people who are interested in biomedical applications, CNT-FETs may have vital role in your future. So, how to design and what to design? These are the two important topic of discussion from this slide onward. In this case, basically, I have proposed CNT-FET based OTAs. At that time, at 45 nanometer technology node, using two different models, reputed models of simulation or designing. And the first model, which was basically used for CNT-FET based circuits. At this 45 nanometer technology node, I know that it is 45 nanometer technologies. We are having lower technology nodes also. Okay, so you may use at lower technology node. Verilog A Stanford model of CNT-FET has been used for analyzing the performance of CNT-FET based nanoelectronic circuits. So this is an important point. Please note down. Here we have used Verilog A Stanford model, which has been developed by Stanford University. That model is very accurate, reliable, trustworthy. And for CMOS, for MOS technology, we have used Berkeley BSIM model of Berkeley University, BPT. Okay, at similar technology node, because while you are going to compare two things, they must be at same technology node. I have reviewed few papers of young researchers, especially the conference paper. What do? They compare two things at different technology node. It's not justified. All the things you can compare apple with another apple of one garden with the apple of another garden. You cannot compare apple with orange of the same garden. So while we are going to compare two things, they must be at same design parameters. This is important. So similarly, we have kept all the design parameters of MOSFET in case of CNTFET. But the model is CNTFET. Very low gauge Stanford model for CNTFET, and VSIM Berkeley predictive technology model for CMOS technology. These are the two things, models which have been used. And using these two models, very low gauge Stanford model and VSIM model, we have designed OTA. And this work has been published in SCI paper, SCI journal. Okay, let us see what has been done and how to use CNTFET, which is CNTFET. This is your ultimate target of this talk. You see here there are 4 different type of OTAs, operational transconductance amplifiers. This is completely CMOS based, which has been designed in all the cases. NMOS as well as PMOS, all the transistors are based on CMOS technology. So we propose another one model based on CNTFET by replacing NMOS transistors only. Okay, these are the 5 NMOS transistors. Okay, which have been replaced by N-type CNTFET based NMOS models. These are the N-type CNTFET models, keeping the PMOS models as it is. So this is one of the design which I have termed as, the first one is conventional CMOS based OTA, where I am using conventional PMOS as sources, this one, and NMOS sinks. Okay, but in this case, the second one model OTA using NCNTFETs. Okay, NCNT, these are the NCNTFETs, and conventional PMOS. This is the conventional PMOS, and it's named as NCNTFET PMOS OTA. Please, you have to remember, if you want to understand the coming slides, please pay a little bit attention. Okay, and time is also fleeting. So NCNTFET and PMOS OTA is this one, and here the reverse process. We kept NMOS as it is, conventional NMOS, and replaced the conventional PMOS by their CNT counterparts. So it comes out to be PCNTFET, PCNTFET, and NMOS OTAs. So this is another model. And finally, in this case, we have replaced all the transistors, all the conventional transistors, by their CNTFET counterparts. So this is also a model. We have designed it. Okay. So all these 4 models have been designed and compared their performances. Okay, now let's see their performance. We know well that while we are going to design amplifier, there are 4 important parameters, which are called performance measuring parameters. Keeping design parameters similar in all the cases, we obtain performance measuring parameters. Though there are 2 things: design parameters and performance measuring parameters. Performance measuring parameter means output parameters, their response. So in this case, there are tens of performance measuring parameters, and among them, the most important are 4: DC gain, power dissipation, bandwidth, and output impedance. So these 4 important parameters have been simulated in graphical form, and the rest of the things are in tabular form. You see here, it is very much clear from this, as we are increasing the number of, there are two things. Pure CNT OTA has highest gain, because as I have clearly told you in the slide of CNTFET that carbon nanotube filter pack transistor is having higher gain, higher transconductance. If transconductance is high, I'm feeling humming, and all of us feeling humming. Anyone who has unmuted, please mute the mic. Okay, let's continue. No. Okay, now see, in this case, what's happening? The gain is high. The gain is high. This high gain models is.
Sir, sorry to disturb you, sir. Sorry to interrupt you.
It is also mentioned.
Nizamuddin, sir, your voice is breaking, sir.
Oh. Is it break? Oh, is it okay?
No, sir, no.
Hello?
No, sir.
Still
Not audible, sir.
Is it okay now?
Yeah, now it is.
Now it is okay, sir.
Okay. Okay, right. No, I was telling you. Please mute your mics. Please mute your mic.
Ayush words.
There
Sir,
are
please
two-
mute your mic. Ayush words. Yeah. Now, okay, sir. Please, sir.
Okay. Now the point number one, there are two things in this graph. Okay, I will go very fast in the coming graph, so let's discuss in detail the first one. You see that in the first case we are having a maximum gain. And the justification for this maximum gain is transconductance. Another important parameter is why the gain is increasing. Okay, along with CNTs. So the reason is n. If increasing n, so of course current will increase. And this is voltage controlled current source. OTA is voltage controlled current source. Okay, we consider the output current. That's the reason that. And in these two cases, you see here, the red one is higher in comparison to blue. What is red one? It is NCNTFET PMOS OTA. Okay. So in this case, NCNTFET PMOS OTA, the number of CNTFET based transistors is higher as compared to PMOS. So of course, if the NCNTFET is more as compared to PMOS, you see here, in this case, we are having 5. Okay, 5. Okay, and these are 4. So is due to this reason, we are having higher gain in case of NCNTFET PMOS OTA as compared to PCNT NMOS OTA. Now let's see, as I have told you, there is a ballistic transport. Due to the ballistic transport, the resistance is minimum or the current is comparatively better. Hello, please mute your mic. Okay, so due to ballistic transport, reduce parasitic capacitance and reduce leakage current, it is having minimum power dissipation. We'll discuss it later on, and it is comparable in both the cases, upper cases. Similarly, we see here the high, in case of OTA, the ideal output impedance is infinite. Okay, and we see here in case of pure CNTFET, it is better as compared to others. But the drawback of this CNTFET is CNTFET based OTAs, it's lower bandwidth. And the reason for this lower bandwidth is high dielectric constant, because in case of CNTFET we use hafnium dioxide. which significantly increase capacitance and reduce bandwidth. Apart from it, it is also having, I have mentioned here, hello, electrostatic capacitances. Now, another important point is effect of variation of CNT diameter. Till now, we have discussed about the variation of number of tubes. Here is the variation of diameter. You see here, diameter variation. Again, the gain is high, bandwidth is low. Similarly, in this case, diameter में power dissipation again low. Or again, the resistance is high. Variation of inter-CNT pitch, gain is high. Okay, you see here SW is equal to n-1 S plus D, and the bandwidth is low due to the same factor. Another is power dissipation low, output resistance high. This is stability analysis. I will discuss it in detail using this tabular description now. इसको जरा आप थोड़ा सा देखिए, मैं full screen कर रहा हूँ इसको. From this discussion and ultimately design parameters, it is concluded that the DC gain is pure CNTFET is maximum due to the high transconductance I have told you. And in case of NCNT PMOS OTA, the gain is better than PCNT and MOS OTA. These are the two important things. And it is minimum in case of CMOS. So from this point of view, the proposed design is having higher gain. And the only drawback is bandwidth. And the predominant factor of the bandwidth is screening effect. There is a screening effect. Okay. Average power is very low due to ballistic transport. You see here, it is 82 nanowatt. We can imagine. Gain is high, power dissipation is low. And ultimately, another important parameter, R out. R out is maximum as compared to CMOS. In all the cases, R out is high. Power dissipation is low in all the cases. All these are the true results which has been simulated using software. If I got time, I will try to explain the software also. I will give you a demo. Slew rate is better. You see here, phase margin is better, gain margin is better. UGF, of course, I've told you bandwidth is low, so UGF is also low. CMRR, which is another important factor, is very high in all the proposed model. PSRR, both type of PSRR are higher. Okay, so all these performance measuring parameters proves that the CNT-FET based nanoelectronic circuits will supersede CMOS based nanoelectronic circuits. This is one of the example. Another example I would like to give you, this is an application of OTA, as I have told you in the initial stage. It is having better result. You see the quality factor is better. Rest of the things are basically design parameters, C1, C2, and upper ones are, the important thing is quality factor, which is higher in CNT-FET based models. Then I have gone through about another model, which is higher version of OTA, cascode OTA. In all these things also, this is the CMOS cascode OTA. ठीक है, इससे फिर हमने तीन अलग-अलग डिजाइन किए. We have designed the three in the same manner. You see, please, especially the new researchers, how to proceed for alternate research work. So, compare all the results with the previous one and among the proposed cascode OTAs as well. I'm going fast because I want to tell you something about software. You see here, this is a comparative analysis of proposed cascode OTA and its comparison with the previous paper OTA. You see here, in all the cases, the performance of cascode OTA is better, except bandwidth, which is the one of the drawback, and rest of the things are up to mark. Again, we have designed this one and seen. This is conclusion. Okay, I did not to go in detail about this conclusion. I want to show you one thing which is very important. Okay, so I just stop. Question answer session will be after 5 minutes. You see here one thing which I would like to tell you. The paper have been published in reputed journals. You see here, Nano, World Scientific Publication, OTA, Design and Comparative Analysis of High Performance. First paper I am reading, Design and Comparative Analysis of High Performance Carbon Nanotube Based Operational Transconductor and Amplifier. It was published in Nano, World Scientific Publication, which is SCI. And second paper was published in IOP Nanotechnology, which is having 3.82 impact factor. It is again, it is SCI paper. And the third one in Journal of Nanoelectronics and Optoelectronic ASP, USA. And the rest of the papers are there. So first of all, before going to end, I would like to give a brief introduction of software with the permission of chair, please. Otherwise, I just stop here. Should I tell you something about software?
Sir, something you can share.
Okay, thank you. Okay, thank you, sir, thank you. Is my screen visible?
Yes, sir.
हाँ, you see here. असल में क्या है? We should share all the things. If you are going to do in invited talk, it is my mentality. Most of the people try to hide the things, but I want to share all the things, because if we researchers of similar field will not share the research with each other, how can we be a competitor of developed countries? If we want to be a developed country, we must share all the research at least with the people of our country. That is my ultimate goal. So I never hide anything. So this is the program which was basically developed of CNTFET. Okay, I would like to explain it briefly. These are the things, similar things. In this program, this is basically the CNTFET. As I've told you, it is a very log A Stanford model of CNTFET. Please keep it in mind. So how to use this model? That is my ultimate target to tell you. You see here there are 4 options of library. Okay, ये library है. इसमें at present we are going to use only one model, and that model is CNTFET model. Level 3, these are the other things. So how to use it? Simply, we will star out all the star means that file will not be activated. Okay, deactivated है. ये 4 models हैं इसमें. इन 4 में से we have used a single one, first one. ठीक है, इसको हमने hide कर दिया है. मतलब it is star means deactivated. Okay, so here in this case we are using CNTFET model. As I have told you, there are CNTFET model and another one is CNTFET model. So here we are using CNTFET model, point number 1. And this simulation work is being done at a temperature of 27 degrees Celsius. Okay, or they are optional parameters, need not to waste our time. Okay, these are the things. Here we will use a supply voltage of 0.9. ठीक है, accordingly ये सब change हो जाएंगे. इसको हमने parameter लिया हमने 0.9 volt, we can change it 0.2, 0.3.
Sir, slides, sorry to interrupt you, sir, slides are not moving.
Slides, no, I'm not moving slide. मैं तो सिर्फ cursor move कर रहा हूँ बेटा.
But here we cannot see the 5 volt which you are telling.
5 volt is not written here, it is written 0.9 volt. Movement of my cursor is visible?
No, sir, no.
No, sir.
Don't know about others, but I am not able to see your moving slide.
Not visible, sir. Cursor is also
Not visible.
कर्सर छोड़िए, आप ये बताइए आपको प्रोग्राम is my slide of program visible or not?
No, sir. No, sir. No.
Then what is visible?
Only the HSI's model. That is the front view of HSI's.
Oh.
Now it is visible. Or
now cursor is visible and it is moving, sir.
Yes.
Only icon is visible.
No, just wait. Give me 5 minutes, please. Give me 5 minutes, please. Just wait. Please, just wait.
Sure.
Just wait. I'm doing some editing. I will show you the PPT. इसके बाद तो कोई लेक्चर नहीं है ना अभी फिलहाल.
Sir, 12 PM onwards, sir. Next session.
Just 5 minutes.
15 minutes you can stand. 5 to 10 minutes.
Yes, sir. Yes.
Arun? 5 to 10 minutes.
Okay. Thank you. Thank you, sir.
Okay. Sir, you are adding the software knowledge to student. We can add 10 minutes also.
Just wait, please. I want to tell you the program basically. Now, is it visible now?
Yes, sir. Now it is visible.
Yes, sir. Now it is visible.
हाँ. अब आप सब लोग please mute your mics and pay attention. This is Verilog A model developed by Stanford University. Okay. In this model, initially we have to mention the title. जो भी आप title use करें, what are the simulation work which you are going to do. It is basically by default we can change it as per our requirement. And later on, these are the options. Here, the most important parameter is temperature. You can change the temperature from here in this model. And these are 4 libraries. Okay. Basically, ये libraries जब आप download करेंगे, उसमें उसके साथ link होंगी. While you will download the model, if you want, I can share you in near future. You can get my number from the teachers, respected teachers of SRM. Okay. So in this case, this model is basically for NCNTFET. तो इसलिए इसको क्या किया है हमने activate किया है. Rest of the models are basically deactivated using this start. Okay. So here we are having 2 models. The first one is NCNTFET model, level 3. Level 1, level 2, level 3, these are the things which I am not going in detail. Later on we can discuss. And this is basically PCNTFET model. So here you are having both the models, but NCNTFET model is activated. Please remember, this is another technique of using these models. Okay, तो क्या है, 2 मॉडल है, NCNTFET मॉडल, PCNTFET मॉडल, लेवल 3. ये अदर टेक्निक है, यूनिफॉर्म मॉडल से ही, मतलब another type of model, uniform model, right? तो अभी फिलहाल हम ये 2 हम डिस्कस करेंगे. Okay, this one and this one. Designing, beginning of the circuit and device definitions. Supply voltage, as I have told you, we are going to change from here also. You can have 1 volt, 2 volt, but it is preferable to use less than 1 volt. So here 0.9 volt has been used by default. You can change it as well. Accordingly, ये सारे voltage change हो जाएंगे. और इसमें ये design parameters है. आपको ये, this is your channel length, 32 nanometer, 45 nanometer, which I have used. Okay. Another important parameter is M or N. I have told you while we were discussing about types of carbon nanotubes. Clearly, I have mentioned indices. So you can change M on N here, और उसके अकॉर्डिंग you based on this m or n, diameter will change, chirality will change using this m and n, and chirality basically changes diameter और diameter changes width. Okay, and मैंने बताया था आपको ये हाई के डाइलेक्ट्रिक मटेरियल यूज करते हैं. ओके, तो इसमें देखिए 4 और ये क्या है कॉक्स 16, तो ये क्या है हाई के डाइलेक्ट्रिक मटेरियल है. उसके बाद इसको आप अकॉर्डिंगली चेंज भी कर सकते हैं या ये भी रख सकते हैं. आप कैसे चेंज करेंगे आई विल टेल यू. नाउ द गेम स्टार्ट्स. दिस इज मेन सर्किट. मेन सर्किट मींस द मॉडल व्हिच यू आर गोइंग टू यूज. ये देखिए आप ये वाला मॉडल. दिस इज द NCNTFET मॉडल और इसका राइटिंग स्टाइल बहुत सिंपल है, बहुत इंटरेस्टिंग है. यू नीड नॉट टू वरी एट ऑल. You see here, in case of P-Spice, this is the advanced version of P-Spice, H-Spice. We are using. I have shown you the display of the software also. So you see here X means new model. M हम यूज करते हैं MOSFET के लिए, if you remember. D यूज करते हैं डायोड के लिए, R यूज करते हैं रेजिस्टर के लिए, C यूज करते हैं कैपेसिटर के लिए. ऐसे we use M for MOSFET, right? तो if you this is not MOSFET, this is NCNTFET, so here we will use XCNT for this model. And फिर उसके बाद क्या होता है, you know well, जो those who are in this field, drain, gate, source, substrate. These are basically the connections. Drain, gate, source, substrate. यहाँ हम we can also use nodes 1, 2, 3, 4. अगर किसी ने किया है नहीं किया है तो I will tell later on. Okay, and then what we are doing here, we are using the name of model. जो भी मॉडल नहीं है, ठीक है. और ये फिर L channel length already we have mentioned above, 45 nanometer, 32 nanometer, 11 nanometer, 7 nanometer, depending on the requirement. Similarly, these are the other parameters. सोर्स की लेंथ कितनी होगी, ड्रेन की लेंथ कितनी होगी, गेट ऑक्साइड कितना होगा, हैफ्नियम डाइऑक्साइड यूज करेंगे या कोई और मटेरियल यूज करेंगे, वो उसका है. डी आउट हमने क्या लिखा है. अब 3 इंपॉर्टेंट पैरामीटर्स ये वाली है. पिच, व्हाट विल बी द पिच. मैंने आपको बताया था क्लियरली, पिच जो है इंटर CNT स्पेसिंग, उस केस में क्या हम यूज कर रहे हैं, हम 20 नैनोमीटर. ठीक है, यानी इंटर CNT स्पेसिंग इज 20 नैनोमीटर, राइट. On this N1 और N2 are M और N. ये डिसाइड करेंगे डायमीटर. देखो मैंने आपको यहां बताया था, इफ रिमेंबर, ये डायमीटर है. M और N से डायमीटर चेंज हो जाएगी. अगर हम इसको M लेते हैं 19, N लेते हैं 0, तो दिस डायमीटर वुड बी 1.5 नैनोमीटर. ओके, तो 1.5 नैनोमीटर ऑप्टिमम है. I have designed all the circuits at 1.5 nanometer. How to consider it? If you are interested, you may call me anytime. Okay, later on. Okay, now the number of tubes. आपने देखा है कि मैंने number of tubes किस तरीके से इंक्रीज किए थे, 5, 10, 15, 16. Okay, तो you can change the number of tubes from here. Tubes. By default it is 3. So these are the 3 important parameters. ये वाली last वाली. We can change pitch from here. We can change diameter from here. और ultimately यहाँ से नहीं बल्कि ऊपर से, जैसे मैंने अभी आपको बताया था, and the number of tubes from this section. So, and these 3 are the important parameters which plays vital role in the performance variation of carbon nanotube filter pack transistor, which ultimately affect the design circuitry. Okay, so in this case we have used this model only. ये वाला मॉडल है. दूसरा मॉडल जो है ये मॉडल है PMOS. अगर आपको PMOS यूज करना है तो these are the design parameters of PMOS. You see here PMOS is written here. Again XCNT, please remember, देखिए यहाँ पर क्या है XCNT और यहाँ XCNT. Both the name should never be same, otherwise you will feel error. ठीक है, तो ये XCNT 1 कर दीजिए, इसको XCNT 2 कर दीजिए. Similarly, you can change accordingly because you see in case of ODA we were having 9 transistors. तो उसमें क्या करेंगे, X1, X2, XCNT 1, XCNT 2, या X1, X2, X3 भी चलेगा, right? We can change these channel length ऊपर से चेंज होगी. ठीक है, ये कॉक्स भी ऊपर से चेंज होगा, टॉक्स भी ऊपर से चेंज होगा, एंड वी विल चेंज द पिच फ्रॉम हियर. पिच और ट्यूब्स यहां से चेंज करेंगे. दिस इज द मॉडल. और ये यूनिफॉर्म मॉडल है, अदर मॉडल. उसके बाद रन करा दीजिए, ये वो सिंपल थिंग्स है. दिस इज ऑल अबाउट योर मॉडल. अच्छा, एक चीज और रह गई हल्की सी, बस 2 मिनट और दीजिए बस. प्रेजेंट नाउ सॉफ्टवेयर. दिस इज अ सॉफ्टवेयर. ठीक है, इस सॉफ्टवेयर में ये वाला है एडिट NL मींस you can see the program. Okay, program के जो results, if you want to see the results of the program, you can see from here. Edit LL. Okay. यहाँ नेट लिस्ट हो जाएगी, जो रिजल्ट आपका आया है, यू कैन सी वैल्यूज. इफ यू वांट सी द ग्राफ, यू कैन सी यूजिंग एवन वेव, क्योंकि ये अभी काम नहीं कर रहा है, दैट्स व्हाई आई एम नॉट गोइंग इन. ओके, क्लिकिंग ऑन दिस, ओपन द फाइल, जहां भी आपकी फाइल सेव है, बट यू मस्ट कीप इन माइंड द फाइल शुड रिमेन इन द फोल्डर वेयर ऑल द लाइब्रेरीज आर एग्जिस्टिंग. ओके, सिमुलेट द प्रोग्राम, see the results of values, see the response in terms of graph. This is all about from my side. Thank you, thanks a lot. It was an excellent session. Now if you want to discuss anything, you're most welcome.
Thank you, sir. Thank you. And we are thankful to Dr. Nizamuddin sir for his wonderful presentation. He nicely explained all the aspects of our CNT, CNTFET, and all other related things. So now I request to participant to put up the queries related to the session of this topic. If you have any query, then you can ask. Dear participant, if you have any query, please ask.
Good afternoon, sir.
Good afternoon, very good afternoon.
Sir, I have one query. Sir, can I do this last signal modeling using the lookup table in this Verilog soft programming?
Yes, you can do.
So how it can interpolate?
Basically, there are two models. One model is based on Verilog. Okay, Verilog model can be instantiated using this H-Spice software, and another one is Spice model. So you can use Verilog model for your requirement.
Sir, I'm using ADS as well as AWR software. I'm not using the Spice, P-Spice or H-Spice software for this large signal and small signal modeling.
So you can use this software.
Okay, matlab it is compatible. This Verilog software programming is compatible with all the software. RF microwave software.
Yes, you can use. No problem.
Okay. Thank you so much.
Okay, welcome.
So there is a query in chat box. How to give a number of distributed equivalent PI network count in H-Spice model?
Where is the question? How to
give a number of distributed equivalent PI network, pi network count in H-Spice model.
Can you write down the question, please? Okay, let me see. How to give a number of distributed equivalent pi network count? Pi network count in H-Spice equivalent distributed equivalent. Actually, what happens in H-Spice modeling is basically based on coding. You can define nodes of a particular circuit, whatever it is, pi model, it is R model. Okay, whatever equivalent model you are using is, you simply define their nodes and write the code. Okay. Any other question?
Any other query, dear participants?
If you are having hesitation, you may ask me later on. My number is very much with all the people, and it is also at the website of Jamia's electronics department. I can also share here.
Okay. So thank you very much, sir. Thanks a lot for a nice presentation.
I tried my best.
Sir, it was excellent presentation, sir.
Thank you. Thanks a lot. Thanks a lot.
Sir, best session, I think. You have shared the hands-on also, and the theory part. Actually, people are hiding the simulation part. How to do.
That is.
That's your scoring. That's the good part, I think.
This is basically not my first lecture. In all the presentation, I share all the things, because if we will not cooperate each other, so what's the benefit of research?
You are a good mentor, sir. That's why.
but the important thing, one thing I would like to add here, as I have told to Verma ji, please, it is advisable to all the scholars, please do not share your research at at student level. During your PhD, you should not share.
Yeah.
I am sharing being a mentor.
Thank you, sir.
Welcome.
Thank you, sir. Thank you.
Welcome
Thanks
a lot. Thanks a lot.
Thanks a lot.
Thanks a lot.
Welcome.
Okay, sir. Thank you very much.
Okay, welcome, sir. Welcome. I am also thankful to you. Thank you. Welcome.
Arun,
Yes, sir. So,
kindly announce participant. Now the next session will start from 12.
okay, sir. So, dear participant, next session will start at sharp 12 p.m.